we spend so little time and so little money and so little effort learning about the way the universe works. For example, the average government investment in science in the Western world is about 0.4% of GDP. It depends which way you look at it, and you can argue. I know in Britain it's about £3.5 billion a year science budget, so you can work that out. So it's a pitifully small amount. And what's begun to bother me is the question, is that optimal in any way? Has it been optimised? Has anyone even stopped to think what would happen if you doubled it or tripled it? And, about a year ago, that was a controversial thing to say, because £3.5 billion or £5 billion, $10 billion sounded like a lot of money. Now, it doesn't sound like a lot of money at all. It's fractions of a percent of the bailout packages. I know in the US that it seems that there's going to be a large increase in science spending. So I want to know whether it's optimised. I strongly suspect it isn't. I know when I asked people in the British government what would happen if you double the science spend, they don't know. Right? They don't know what the impact would be on GDP, on our quality of life, on the rate of discovery. And with that, actually, goes an interesting question, which is, if you increase the amount of, let's say, taxpayers' money into science, then what's the responsibility of the scientists back to the taxpayers again? How should government direct scientific inquiry, given that they spend taxpayers' money on it? So should you follow government priorities? In Britain, which I'm sure is the same as the US, it's things like energy security, climate change, ageing population, those things. But when government direct scientific research, it's my opinion, and this is not necessarily true, but it's my opinion, that it rarely works. Right? If you look at paradigm shifts, the big scientific discoveries, and you can name them, or your penicillin, or the transistor, or nuclear power, or solar cells, anything you want. I struggle to find one that came from directed scientific research. Right? They're chance discoveries, and it's not surprising to me, and it's actually obvious why that is. Here's the known, and here's the unknown. I'm not trying to sound like Donald Rumsfeld. I'm not going to do that. So the unknowns here, the knowns there. If you populate this border with lots of people who are free, and allow them the freedom to just investigate, then it seems obvious to me they're going to make more inroads into the unknown more quickly. And the more you constrain them, the less freedom you give them, because you're concerned about the funding and you're trying to direct what they do into precise areas, then the less inroads you're going to make. So I think what's exercising me is how do you convince, because I'm convinced it's a good idea, how do you convince a government to invest properly, not at 0.4% or 0.5% of GDP, but let's say 2% of GDP, which is still pitifully small, in science, without constraining the freedom of those scientists. And so you'll get the next wave of paradigm shifts that will make the world better. So that exercises me. Scientifically, I work at the LHC in Geneva, the Large Hadron Collider, whose job it is to take the next step in what I think is the main road of physics, the main line of physics. So the LHC's job is to understand the forces of nature and understand the building blocks of the universe, the smallest building blocks of matter. In that respect, you can draw a line from Newton. So the first modern theory of a force, gravity, and you can go on to Maxwell, building on the work of Faraday. So the forces of electricity and magnetism unified together, you get the theory of electromagnetic waves. Right? You get the speed of light being a constant in that theory. That leads to Einstein, E equals mc squared. You get the theory of the weak and strong nuclear forces. The LHC is the next experimental step on that road. So we've been stuck for arguably 40 years, actually. It's 30, 40 years since a big new idea emerged on that road. And we've been stuck at a particular point, which is the origin of mass in the universe. So this is what the Higgs boson is supposed to fix. Right? But to many people it looks like particle physicists just looking for another particle. Spend $10 billion, we look for another particle. It's not that at all. The question of mass in the universe is dictated by the place that we've become stuck. Right, it's the door that's closed. And if you have time, I can go into some depth and detail about why that is. But the point is that we know exactly where to look for the origin of mass. We know what energy to look at, what energy of collisions we need. If you want to think of it this way, we know how far to go back in time to the Big Bang to look. The LHC has got plenty of energy to do that, so it will discover the origin of mass in the universe. But that's not an end in itself. That's the door on the main road of physics, which will open when we discover it. And it should be, what would you say, 3 years maybe, 3 to 4 years, I would guess, if the LHC performs as we'd like. I mean, as you may know, we had some issues. We blew a little bit of it up after commissioning it. But the schedule at the moment, as I speak, in February 2009, is that all the refurbished magnets, we damaged about 50 of them, will be back in the LHC in the end of March. The LHC will be commissioned in September and begin to take physics results in October and run for a year, which is unusual for CERN. Actually, CERN rarely takes data over the winter, but we're going to run for a year, and so we should really have, it's pretty much caught up to where we should have been anyway by autumn 2010. So it's an exciting time. It's actually the first time, certainly in my career, and probably for 20, even 30 years, that you could guarantee that you've got a particle accelerator that has enough energy to discover something profound, which in this case is the origin of mass in the universe. Maybe Higgs, maybe something else. In fact, my most cited paper is called WW Scattering in the Absence of a Light Higgs. So there's my cards on the table. Now, if you decide not to allow or to request that politicians do not direct the direction of scientific research, then the question arises, well, who does it? Right? If somebody's got to allocate the billions of dollars that are spent on scientific research of public money every year. Scientists are good and bad at doing this. I think that scientists are very bad when pressure is applied to them, because scientists are clever and scientists are good at playing systems. And so if you put a system in place, then the scientists will go and get the money. And I think there's a huge danger of scientists trying to second guess government, right? And you get into a vicious circle. So let's say government say, we want particle physicists to have an eye on the big questions of the day. So let's say energy security, right? And there's some overlap between particularly fusion research, big science projects that require big magnets that are similar in many ways to the magnets we use at the LHC. There's some overlap there. And so what you can see is that a scientist in a university whose salary, particularly in the US, but also in the UK, and professional standing is based on the amount of research income they get, they will build research projects that they think government, or at least the funding agencies, will respond to. So the direction can often be accidental. There's a snowball effect, and I've seen it in the UK actually. I've seen, obviously, a politician like a science minister will say that the government has priorities, and it doesn't really think about the impact that will have further down the food chain. But people listen for some reason to politicians really carefully, and then they pick out the little nuances as they see them, and then start modifying their behaviour. And before you know it, you have an intensely directed and narrowing science programme, which nobody really intended to generate. So what you need, actually, at the top of science, is you really need people who are not in awe or overwhelmed by the political process, and also you need people who don't enjoy it, actually, because it's really quite enjoyable to start mixing with the powerful and trying to understand. And I've seen it. You can get into a mindset where you think, I know what these guys in Washington or London are thinking. And you start manoeuvring, and you ruin the science program, right? So you need before the last US election, I would like to use the word maverick, and I'm not going to do it. But you need something that you could describe using that term to really you need people who believe that scientific investigation is most benefit to society when it's free, right? And don't believe that politicians are the people who can maximise the benefits of society through the direction of science funding. There are 10,000 physicists and engineers at CERN. Many of them are not there permanently. The population in Geneva fluctuates. There are 85 countries around the world. Physicists from all those institutes collaborate either on the data or in building the hardware. And it is a wonderful place because its commitment to blue skies research, to undirected research, is absolute. And there can be no better symbol of that pure curiosity-driven research than the Large Hadron Collider. It has no use, in inverted commas, other than to further our understanding of the universe. And if you want to defend the Large Hadron Collider, then the best defence, I think, is that understanding the way the universe works has never been a bad idea. Right? That's history tells us that. So it is one example of somewhere that's CERN itself is very free, and its constitution is free. It came out of the Second World War. It was an international institution built to participate in the cultural regeneration of Europe. It came from, actually, I think that the first conference that was mentioned was 1949 or something like that in Lausanne, but it was founded in 1954 officially. And the Constitution says blue skies research with the peaceful pursuit of knowledge, I think, is in the Constitution of CERN. It's a wonderful place. But then, actually, at the national level, then it changes a little bit because the particle physics budgets then become subject to the political kind of manoeuvrings of the day in particular countries. Again, CERN has got a huge advantage because it's protected by international treaty, certainly amongst the 20 European member states. So there's a kind of a story, it may be apocryphal, but in the 80s, in the Margaret Thatcher's government in Britain, who were very aggressively looking at all government spending, looked at pulling out of CERN. But the UK contribution to CERN today is £80 million a year, and that's an international treaty. And it is far too much hassle to pull out of an international treaty for a government. The cost-benefit ratio of causing the trouble just seems to be too much, and that's the story that you hear. So it's a very small budget, actually, if you think about it. It's about the budget of a medium-sized Western university. It's less than $1 billion a year in total. So once you arrive at CERN and you're part of one of the big experimental collaborations, the four of them, Atlas, CMS, LHCb and ALICE, around the LHC. The work that you do within that is divided into two bits. Right? There's all universities play some role in maintaining the hardware. So there's a serious bit of science and engineering to do. So the bits of hardware, the bits of the detectors are built in the universities around the world, and that's your responsibility. So you have an organisation to do that, and that's the kind of serious day-to-day bit. The other bit is when the data comes, which is what everybody's in it for. And then you have complete freedom to do what you want with that data. So anybody on the collaboration can look for anything. And actually, one of the great challenges for people who manage at the top of these collaborations is to try and make sure that not everybody goes and looks for the Higgs particle, for example, because there's a ton of physics to do. We've never collided particles together at these energies before. So, but you can only use coercion, right, to do that. It's an interesting management challenge, actually, because you want to cover the whole of physics, the whole of the physics you can do. And actually it gets covered, because, see, physicists, there are different characters in experimental physicists. Some of them like to work on the big questions, which by definition will have a big team. So if you're looking for the Higgs, there's a huge working group at Atlas, let's say. There are hundreds of physicists from 10 to 20 institutions all working together to do it. Or you can go into a little corner, a kind of more esoteric branch of particle physics, and you might be working on it on your own with a couple of grad students at your university. And fortunately, because there are lots of different characters, it seems to balance out quite nicely, and there are enough people to do everything. I mean, I personally tend to like to drift off into slightly more esoteric corners. I like to work a little bit on my own or in a small group. I do two things. One is I lead an upgrade project, a hardware upgrade project, and the aim is to put these little detectors, literally about that big, half a kilometre away from the point where the protons collide at the LHC. And this is to take advantage of a really interesting process called central exclusive production. So basically the protons come in and they can glance off each other and they can stay intact. Right? So you get 2 protons in, 2 protons out, lose a bit of energy, and all the energy they lose can go into the production of a single object, which you'll see in the main detector. So that could be a Higgs particle. So you get PP goes to PP Higgs. Because these protons lose a bit of energy, when they go round the corner in the LHC, so they go through the magnets, they get bent a little bit more because they're going a little bit slower through the magnetic field. And so they get bent out of the beam. And at half a kilometre away, if you can get little detectors in to about 5 millimetres from the LHC beam, which has the energy of an aircraft carrier going at 30 miles an hour, by the way, so you have to be careful, you can grab these, so you can detect them. And if you think about it, if you can just detect both of them, then you can measure exactly how much energy got lost, because you know where they are and how far they came out of the beam. So you can measure the mass of the thing in the central detector beautifully accurately to really high precision. Also, you can only make particles in the central detector that have particular quantum numbers, so particular properties. An obvious one would be that it couldn't have electric charge, because if you had 2 protons going in and 2 protons going out, then you can't create electric charge in the middle, so it would have to be a neutral thing. So it turns out that in this process, if you see a Higgs particle, you immediately know what its properties are. There are other properties as well you can infer from this process. And it's one of the only ways anyone's been able to think of at LHC for measuring the properties of the Higgs. Right? So you can detect it, and you can see what its mass is, and you can discover it, but you've also got to measure what it is to show that it is a Higgs, or it might be some other kind of thing. So this was a process that really myself and a few colleagues in theoretical physics worked on about 10 years ago, 8 years ago. So the thing is, when we built the LHC and designed it, we didn't know really about this process. So so you ask the question, well, could we add them in as these little detectors as an addition and use this process? So that's going quite well actually on both 2 of the big experiments, Atlas and CMS. That's through the R&D phase and into the kind of final development phase. So that's my hardware thing, and that was kind of my idea. So I was going to lead that on both collaborations actually. Then the more standard physics, I'm very interested in. So that's Higgs. I'm very interested in what happens if there isn't a Higgs, because the great thing about the LHC is that it has enough energy to discover the mass generation mechanism, whatever it is. Right? So we know exactly what energy our theory, the standard model of particle physics, breaks down and doesn't work without a mass generation mechanism. It's 1.4 TeV in particle physics units. The LHC has 14 TeV, so it has plenty of energy to go to that point. And it breaks down in a very specific place, which is, there are particles called W particles, and they carry a force called the weak nuclear force. That force is the force that allows protons to turn into neutrons in the sun. Right? So the sun works by taking 4 protons, 4 hydrogen nuclei, and making a helium nucleus, which is 2 protons and 2 neutrons. So the sun has to turn protons into neutrons. And the W particles, the weak force, does that. So it's fundamental to the universe, but quite esoteric in that we don't notice it here on Earth very much, unless we look at the sun. So we do. We don't know we're noticing it. those things, those W particles, are very heavy. Right, they're 80 times as heavy as a proton. Right, so it's heavy as a nucleus of gold or something like copper, let's say, something like that. And it's in that is the piece of the standard model that really requires the Higgs. Right, it's particularly the matter particles are not too problematic for you with giving masses to them. We think that goes through the Higgs mechanism as well, but it doesn't matter as much. But it really matters for the force-carrying particles. Having massive force-carrying particles is a nightmare for the mathematics and the beauty of the theory. So it turns out that when you collide those things together, which you can do at LHC, you can have some protons going along and they can emit W particles and they can bounce off each other. It turns out that that's the most sensitive place to look for the origin of mass, whether there's a Higgs there or not. Right? So it's the process that you want to look at. So I've done a lot of work on looking at what happens if you make no assumptions and you just go and measure. You look for WW bouncing off each other in the detectors at LHC and just measure it without prejudice, right? Without any assumptions at all. Make a measurement and look, because then you don't bias the results at all. And it's an interesting process, actually. And you can, most models, even models that have extra dimensions in the universe which can explain mass generation, whatever you want, you can see it in that process. And I could give you a more technical answer for the connoisseurs if you want, but it's a beautiful process.